from home. No worries, we all understand.
Great.
Benji, if you want to take control and share your presentation, I'm gonna make a little introduction for you.
Great. Is that visible?
Yes, we see this. Okay. So the following invited speaker is Benjamin Rosman. He is an associate professor in the University of Witwatersrand. He is active researcher in reinforcement learning area, particularly applied to developmental robotics. So, well, welcome, Benjamin, all yours.
Thanks so much. And it's great to be here. Thanks to all the organizers for inviting me. You know, obviously there's the benefits of, this is the one positive of the current global situation, is that we can get together in this remote setting. The downsides, obviously, my internet connection has a sense of humor. Cool. Yeah, so I'm here to talk about one stream of work that we've been doing. Some of the projects of some of my students, really about human-robot collaboration. And sorry, can you see the transition there? Cool. Okay.
Yes, we see it.
So when I talk about human-robot collaboration, I've got this kind of scenario in mind. You imagine that there's a human that's got some sort of task and a robot working alongside them. So perhaps there's some sort of conveyor belt, and you can imagine some tasks maybe are better suited to the human. Maybe these are more fragile things it's got to pick up off the conveyor belt, and maybe the robot has its own tasks assigned to it. And so, you know, we want them working alongside each other. And when we talk about collaboration, there's a few things that come to mind as desirable properties. We obviously talk about the robot and the human having shared goals. We want their coordination to be fluent, although in a lot of the work I'm going to be talking about now, we assume that there isn't much direct communication between them. And it would be nice if the robot could help the human if that's needed at all at any point. And then specifically, I'll look at these two settings. The one is where you've got a direct collaboration. So what I mean by that is, in this case, the robot and the human are working together and they're both kind of operating in the same space. Right at the end, I'll touch on a different setting where there might be some sort of advisory role that the human's playing to guide the robot in the task the robot's trying to accomplish. Now, the big challenge that I'm going to be focusing on in this work specifically is that humans are, I guess, human, unreliable, make errors, dynamic, and that sort of thing. And often what you'll see in the literature is that we don't make these assumptions. And this goes back to even the days of focusing on game theory, where, you know, assume an optimal, rational opponent. And while that's good under some situations, it's obviously got limitations. We also see this in a multi-agent reinforcement learning setting where if, you know, the policies of all agents are stationary, then you can proceed as you would like. But if one agent's learning, then that tends to throw a bit of a spanner in the works. So, you know, one way you could go about thinking about this problem is you could define something like a state machine for the robot. So we could say, for example, there's tasks assigned to the human or the robot, and, you know, maybe based on some observations, we could say, okay, the human seems to need help for its current task. We might have a situation where the human could kind of warn the robot off and say, stop interfering with what I'm doing. And then based on this kind of simple interaction, the robot, you know, if it's the robot's task, it does what it needs to do. If it's a human's task, the robot sits around idling until it sees the human might be in this state that it needs help, and it takes over to solve the task. Right, but again, like the challenges that come up here is what happens if there's unusual behaviors or human errors or something like that. And, you know, I've got a little demonstration here where you could imagine that there's a box coming along, and for whatever reason, in this case, it might be because the human seems to have two dislocated shoulders, the human's unable to pick up the box. And the robot might say at some point, okay, I think we're in the state of the human needs help. Now, planning might be quite slow, so the robot tries to plan and the task ends. Right, so being reactive in this way doesn't necessarily help us for the kind of fluent interaction that we'd be looking for. So what we could do instead is think about modeling the human. And what this would mean is to try and predict the internal state, or what's going on in the human's head in this case. And what I'm going to talk about here is largely a series of papers that were produced by a student of mine, Jean, and it was really trying to get at this question: can we predict what's going on with this human? And by internal state, there's a number of things we could do. Obviously, we're not doing the full theory of mind here to figure out when he's thinking about lunch, but there might be some kind of coarse categories of behaviors or mental states we might be looking for that would affect his behaviors. So this could be the human's bored or distracted, or perhaps struggling with the task. So to do that, we obviously have to model the human, but the challenge is that learning models is famously difficult and requires a lot of data. Now, I'll talk a little bit further, but one of our aims for this project was to take this to work with actual real humans in a physical situation. And it doesn't take long to figure out that you can't collect enough data from a human in an interactive task to actually build your model. So the approach we can take is twofold. Well, it has two components. First, we can build and evaluate our models in an offline stage beforehand. And then we can do some sort of behavior inference or selection in an online phase. And this is really the theme I'm going to talk about going forward. And as I say, the kind of real question here is, can this actually work if we're looking at interacting with real humans rather than just simulated ones? However, the focus of starting off with this is to simulate the human, right? If we need more data, this seems a reasonable approach to take. And actually, the previous speaker was talking to this as well. So one way we could think about this is to model our simulated human as an MDP, where we've got a number of different states that the human could be in. This is really to generate behaviors of the human. Now, if you've got a whole lot of different states talking about, there might be, we're simulating different phenomena, that maybe the human's not paying attention at certain times, or that it's tired, maybe it's successfully managing its task, and so on. We can change the transition probabilities here to reflect different types of human behaviors. And actually, a lot of these ideas and the way we set this up was very much inspired by workplace studies on humans. Again, when you're modeling something that's to some extent in the head of a human, it's not going to be perfect, but we can base this on studies of what people seem to do. And the point of this is we can then, in an interactive scenario, kind of take samples from this model. And that would describe how the human reacts to certain things the robot might be doing. It can tell us, with what probability the human might switch to a state where it's tired or not paying attention to the task, and so on. So this gives us a simple way of simulating a human. Going forward from there, we can now think about what happens on the side of the robot. Well, obviously, the idea is that the robot doesn't have full observability, can't see these internal states. And so we can model this as a POMDP, partially observable MDP. And we took a few steps that we followed here. Now, there's a whole kind of flow diagram that we used in our final experiments, but the basic idea is as follows. We can start off by hand coding the structure of this model. As I say, this can be based on some workplace studies. There's a fair bit of that in the literature. And then what we can do is in our robot POMDP model, by interacting with the simulated human in environments, as I showed earlier, we can kind of learn the probabilities and learn these POMDP models. And we can do this for different kinds of humans that we developed in simulation through changing these probabilities. So we can fundamentally generate thousands of different types of simulated humans. And we can learn kind of response models to these based on, like in this POMDP model setting. And then we can do this, the standard thing in machine learning, where we can, on some validation data, again, we generate some more human models. We select ones that seem to be quite promising, and again, fine tune them, these parameters on these additional models. Right, so the question then is, which of these models perform best? We can evaluate that in quite a straightforward way. And in fact, I'll talk a little bit more later on about doing this on real humans. And we can do a similar thing there. Based on some promising models, we can then validate in some early trials on some humans to see which models tend to perform the best in those situations. Once we've got a promising POMDP model, we can then run it online on new humans, whether these are more kind of randomly simulated ones or real humans. And we can use a POMDP solver to generate our policy in an online way as the interaction is progressing. So if we had this kind of model before, we can move to something a little bit more complicated. It's still got the same basic structure of, your task could be assigned to the human or robot. We could do some sort of inference that the human needs help. Maybe the human can stop what the robot's doing at any point. But the way to think about this is we're doing some sort of inference of like the human state of what's going on internally with the human. And based on that, we can choose our intervention, again, using the POMDP solver. So there's a bit of a caricature here, but this gives the idea of the extra information that we inject into the original model. And now we've got these two kinds of models. We've got the original reactive model, which we're running as a state machine, versus this proactive model, which is a POMDP model trying to do some inference on what's actually going on with the human. And that's been seeded based on all this training and simulation. So let's look at kind of what the difference of thinking about it in these two different ways are. Well, first, what we can do is look at the effects of a human acting alone versus acting with one of these two other models. You can see here that generally over time, but we've set this up that the human will become more fatigued over time. And so the success rate, this blue line, would drop over time. And the inclusion of any of these assistant robots, which we'd hope would increase the task success. But doing this proactive thing kind of gives us better cumulative rewards over time. It's less impacted by the fatigue because it's been trained on a broader set of models. Actually, we can look at some kind of more concrete numbers, and we can see on the metrics we care about, the total reward, average over a number of tasks is improved. We get fewer warnings of the human interrupting the robot doing something wrong. Our task success rate is up, and the task duration is reduced as well. So again, in our somewhat funky simulation here, you can see with the same kind of environment, with the same condition of the human struggling with the task, the robot actually starts planning much earlier. It's not as obvious as it should be because the planning does take a while here, but it manages to grasp the box before the conveyor belt continues. So the idea is by doing this kind of modeling, we can get an idea of what's going on and preempt what might be required. Now, I mentioned this aspect of fatigue, and we could say actually maybe there's more going on in the space that can talk to some sort of longer term adaptation. And this really comes in with what I mentioned earlier about non-stationarity. So you could have these phenomena where the human's changing over time, becoming more and more fatigued. It could be learning, and we could even have a situation where the human changes in this task. One human wanders off from the production line and another one arrives. So we can think about this slightly differently. And the idea is maybe we can adapt. Instead of having one model that we're working with, maybe we can reuse a bunch of different models. And the idea is if we have these different human types, which are effectively profiles of human behaviors, maybe we can do something to identify what the best existing one that we know something about is and adapt to select this at the right time. So fundamentally, the caricature of this situation is, the robot's interacting with a human at the moment, but it's going to try and match it to one of the models that it knows something about before. So we had these kinds of models before. Then this process involves taking a whole lot of them that are different and building a policy library. And I'll talk a bit more about that. But in our policy library, we should have an idea that there's a set of different models corresponding to these different human types. For each one, we've got some idea of what an optimal response to that might look like. And we could have an idea of the kinds of observations that come out of this model when it's executed. So for example, if one of these models was corresponding to a human that was very sleepy, maybe we'd see different kinds of observations to a human that tended to wander off from the production line quite often. So you'd imagine the kind of interaction between these models and the robot policy would produce different observations. Again, some humans might be more prone to interrupt the robot and others would be happy to let the robot take over. And all of this would be learned again in some sort of offline / simulation phase. So the way that this works, our model is called adaptive Bayesian policy selection, is during learning, you've got a type space that corresponds to many of these human types. So fundamentally, each of these you could think corresponds to different amounts of different characteristics that we might care about that gets coded back into these original models. And as I said, each gives us different observations that we could be expecting to see when those models are run. And from those models, we can train a policy library with an optimal policy for each one. And in addition, we need a couple other things. We learn this observation model, so we get the observations conditioned on this type and the policy. And we get a performance model, which says how well does this combination of type. So we need to learn these few things, but what we're going to be doing then is in an online setting, based on the observations we receive, we can do some sort of Bayesian belief update over the set of types to better localize the type of the new human that we're interacting with. And based on that localization, we can then use Bayesian optimization to choose the best policy from our library to respond to that. So the idea here is that based on these observations, we're going to try and do very fast inference to let us choose the best policy to use at that point. Now, the point here is that it's not about choosing an optimal policy, it's about choosing the best from a library, which is going to be a much faster operation than learning that policy online. So this is based on this idea of model reuse. So again, we have a set of candidate models with some distribution over them of which one we think we're currently interacting with. Each one could maybe have an optimal policy associated with it. And based on this belief, we choose whichever one seems to be the best one for this case. We apply that to the current human. That will give us some observations, and we use that to update the beliefs. So while we're executing this policy, we're collecting the observations and updating our beliefs as a result of that. So again, we tried this out in simulation. And again, we can generate a whole lot of different human types. So you could imagine some sort of setting like this, that after some number of tasks, we provide the robot with a new human, or we drift the probabilities over time. So for example, you could see here that each one of these might correspond to, say, some human profile that's, in a distracted state for some period of time and warning the robot for some period of time, different characteristics fundamentally. And what we see there is that running this procedure gives us a good learning curve that gives us a reasonably consistent reward here, but that beats what you might have done otherwise, which is kind of in hindsight, choose the best single policy, which is kind of as we did in the previous work. So given that set of human types, we could have chosen the best policy and just run that. And so regardless of what the best policy was, you can find that doing this adaptation gives us a better performance. And in fact, again, on all of the metrics that we care about, it does better than having a single policy, regardless of what that policy is. So this includes higher rewards, fewer warnings, a higher task success rate, and the tasks tend to run shorter, which you'd expect by being more proactive in this interaction. Now, as I said, we also tried this in a lab setting, and I'm sure everyone's familiar with the idea of doing these kinds of experiments with real people in labs is a complete pain. So the way that this was set up is we had this cute little conveyor belt over here with a set of cubes, and we had tasks that we gave the human, which were to place the cubes in 3 collection bins in different ways. There was a robot arm that was collaborating with the human. The human was wearing this funky hat and gloves to try and get an idea of what the behaviors were. And then we had a screen over here that at the beginning of the task described the task constraints to the human. Now, it's very difficult for this kind of setup to do something where the human might experience fatigue over time, because I can't imagine anyone getting fatigued picking up these blocks. So what would happen is the task would be some sort of strange configuration like this, that the first object maybe goes in the green container and the second object in the blue container and so on. And we could set up a whole lot of tasks here saying, from the simplest, which would be put red objects in the red container, down to these kind of very complicated permutations. So just to show you an example, you have something like this. The robot picks up the blue, the human warns it off, says put it back, then the robot stands back and the human could carry on with the task. So the idea was that this should be a cognitively challenging task rather than a physically challenging task, so there'd be a reason for the robot to need to intervene in what the human was doing. And this was quite a pain to set up. All right, so looking at the results from the two kinds of settings that we had, first with the proactive versus reactive robot. So we found, again, the same kind of things, that from the human alone acting up to using one of the robots, we'd see a jump in about 20% task success. But it was more notable on the proactive robot. Task efficiency was increased and the warnings was dropped dramatically. And we did asked a whole lot of questions to our subjects throughout the experiments. And we found that again, the metrics we're interested in, we'd see a more positive score from the human. So for example, they felt that this robot was better able to anticipate their needs and took over at the right times. They trusted the robot, they enjoyed collaborating with it, and so on. So again, these are quite difficult kinds of experiments to conduct, but this seemed to show that people felt that the interaction with the proactive robot was more fluent than just acting reactively. And when we moved on to these long-term adaptation tasks, which was a much longer task that we would run with the human, they had to repeat these tasks over a very long period of time. What we found was that despite fatigue and things setting in, the performance, the reward would increase, and we'd see that consistently the robot would be changing the policy that it's using throughout the trajectory, and the warnings received would decrease over time. And this correlates with, as we looked at the ratings from the people as they progressed, they ended up trusting the robot more, they felt that it anticipated their behaviors better, took over at the right times, and so on. So this really gives us a picture that we can think about these models, which again are just going to be approximations for what's going on. But if we can kind of infer that there might be a need for help, then that's positive. And secondly, if we can adapt policies based on the observations we're seeing and select them from a library, it doesn't matter that we don't perhaps have an optimal policy. We might have one that's good enough that we can apply it to the current situation. So finally, I just want to turn attention a little bit from looking at the setting where the human and robot are kind of collaborating as equals almost, to if there's an expert advising the robot. Now, you would have seen this probably in the discussion of my student Tamlin earlier this morning. So I'm not going to go into full detail here and just give an idea of how it fits into the picture. But if we've got an expert collaborating with our robot instead, this looks like something like this. So there's a setting, maybe there's a robot that's trying to look after this guy over here. We've got a panel of experts that are advising it based on what's going on, and that lets it choose its intervention. Now, this is great if all those experts are reliable, but in many cases, they might actually be human and so not completely reliable or give us bad advice at some point for various reasons. So assuming our experts are not reliable, what do we do about that? In the case of the direct collaboration, we model the relevant hidden states of the human. But in this case, the kind of variable that we care about is their reliability. So what do we do there? This interactive setting, we've got the standard RL loop of the agent with the environment, but the experts, based on the state and rewards, can give some advice. Internally, we want to do some sort of modeling of what's going on, and we think about the model here as, again, the feature of interest in this case is the reliability. How much should I trust each individual expert? And so that would be the model that I want to learn. And so the basic idea here is if this reliability comes down to the probability of giving the correct advice, then for every decision we're making, given some advice, we're going to compute the probability of an action being optimal. This lets us leverage the wisdom of the crowd rather than just a single expert. We choose the best action based on that. And then based on the outcomes, we update our reliability measure of each expert. And when we look at experiments, if we had, say, a single reliable expert, you can see over time we learn to trust this expert. In the case of a single unreliable expert, we learn not to trust this expert. And that gives us the desired performance. So in this case, the blue line would just be an agent doing some standard learning with no advice. The green line is a naive agent that follows all advice. In the case of a perfect expert, we do slightly worse than that because we're inferring the probability as well. But in the case where it's an unreliable expert, we don't end up taking this bad advice, and we converge as with the baseline agent. In a more complicated setting where there's a whole panel of experts, we find that over time we can learn to infer kind of the correct ordering of how much we should be trusting each one. And again, this gives us improved performance over the other agents that are just the baselines. So tying this all together, collaborating with humans causes issues for all the factors we've discussed: the imperfect knowledge, the noise, the errors that they induce in the problem. And so one way to deal with this is to model the human. To get around this issue of requiring a lot of data, we can use a number of different strategies, including learning models and simulation, and then doing a small amount of fine-tuning on actual humans. We can learn a whole lot of models offline and then select them online quite rapidly in a probabilistic way from a library. Or we could do something like a lightweight proxy for the model, which might just involve a model of reliability. And obviously a single parameter model is much easier to learn than something more complicated. So thank you very much. I hope that was interesting. I know it was quite quick, but yes, hopefully this gives some ideas.
Thank you very much, Benji. Thank you very much. Very interesting talk. Let me check if we have any question. We have time for a quick question as well in the chat. Is there any? Not at the moment. Well, I want to ask you about, well, future possibilities of this approach. For instance, well, this is normally used in, for instance, human-robot interaction. Mm-hmm. For instance, as you or your students show, to use as advice, things like that, no? Mm-hmm. But it's. Do you think that can be used as well in this simulated human interaction approach, sort of? And if so, do you think that the trust that the human can have with the simulated user, how would affect the possibilities in terms of the advice received by these simulated users?
Sorry, so you say in the case where you've got a simulated user and the real human?
Yeah.
Yeah, so I think so. I mean, again, you want to kind of boil it down to what are the factors of interest. So a big theme here is about trying to distill the model down to something that can be learned quickly. So we've been thinking about this, you know, in industry, they're quite keen on these what they call it, robotic process automation, which is a terrible use of the word robot. So you might have, again, in that kind of interactive setting, sitting at a computer desktop working with your Excel spreadsheets or something. Again, you want to try and not disrupt the workflow. So I think their trust is an important factor. And we touched on that a little bit in two different ways. One was in those user studies. We kind of asked them how much they trust the robot, but that's a fairly lightweight measure, not really going into, you know, in a complicated setting, which would they choose to help them. This is something we want to actually look at further, is to say, if you've got a number of these different robots trained with these different strategies, can we get people to effectively put their money where their mouth is and say, like, I would rather collaborate with this robot over than, say, even in the best case, another human, because from some interactions, I trust that they can, you know, infer what I want out of a task better than I can. Where I'd like to take this ultimately is to the setting where, you know, you're say working on a task in say an assembly situation. An ideal collaborator might get you your screwdriver before you get to the point where you need it. So there's a lot of other information that would have to come in for that to work, which is maybe learning more about the task as well. So in this case, the task was pretty fixed, but what was being learned was the human. And I think the next step forward is talking to the kind of orthogonal problem of learning about the task and the human simultaneously, figuring out how to tease those two factors apart, so that it's more flexible in the kinds of tasks it can solve.
Okay, thank you very much, Benji, for your talk again.